We're given the masses of the two objects here, or I'm just going to write them as the weight. First, we're applying a force of 300 newtons to that spool. The weight of what I call C, that'll be the block, is 491 newtons. And the weight of the spool, I'll call that WB, 392 newtons. And again, we want the minimum values of mu A and mu B to cause motion, or be on the verge of motion. We have the two objects, the block and the spool, that we want to model. I'm going to, it'll seem a little counterintuitive, but so it matches my notes. I'm going to start with the spool and then work my way up to the block. So I'll just draw the skeleton of the block, but work on the spool first. On the spool, we have the applied force to the right of 300 newtons. What other forces are going to act on our spool? Right, it's resting on the ground, so there'll be a normal force there. I'll call that NB. The block resting on here. We know that NA will be pushing up on the block, so NA must be pushing down on the spool. Oops. Let's hold off on the friction for right now. What was the other force on the spool? Right, its own weight, which for the spool is the, I forget, the 392. Applied force, the two normals, we know the direction of the normals for certain, and we know the direction of the weight. Now we have to think about the friction that it's going to experience at those contact surfaces A and B. Let's start at B. That'll be the easier case. In the first scenario where it's rotating, we think it might rotate counterclockwise. What direction should the friction point at point B in that case? So which direction does the point at B want to move if it's rotating counterclockwise? Right, if it's rotating counterclockwise, this point wants to move tangential to, it wants to move to the right. Therefore, the friction would oppose that motion and point to the left. I'll call that F sub B. And if it's rotating counterclockwise, then at A, what direction should the friction be pointing? In this case, to the right, because the point up here, if it's rotating, the point wants to move to the left. The friction is going to counter that by pointing to the right. So FA, if it's rotating, is going to point to the right. Before I go back to picture one, think of the other way that we thought motion could occur. The entire spool slides to the right, in which case, what direction should the friction point at B? Right, it should still point to the left if the whole thing is sliding. However, at A, if the whole thing is sliding without rotating, now this point wants to move to the right. Therefore, the friction will be pointing in the other direction. We didn't see this occur before where the direction of friction would be flipping in that crate problem or in the 3 blocks stacked together problem. Whether, depending on which block was sliding, did not change the direction of the force of friction. In this case, though, the two different methods of motion actually flip the direction that friction should point. So it's actually at the free body diagram level, we're going to have to change something between the scenario A, which I'll call the rotation, versus scenario B, which I'll call the sliding to the right. I'm going to keep right now for the rotation theory and see how that plays out. Based on picture 2, I now said FA must be to the right in this picture. Therefore, FA must be to the left in picture number 1. We know this. We know that this block has a weight of this one is the 491 newtons. And now the way that C is situated, I'm going to make an assumption here that it's not wedged in between the wall, that it can freely slide up and down on those rollers there. So what's going to happen is the block is going to be forced either to the left or to the right. But in this case, there'll be a normal force from the wall, but actually the left wall or the right wall could either one exert a normal force, which is different than how the ground works, that the ground can only push on you, it can't pull you. In this case, either wall could push. I'm going to model the pushing from the left wall because I know that FA has to point to the left because it points to the right here. Therefore, the normal force at C will point to the right. This is a case where the normal force could be positive or negative, and it would be okay because it could push or pull the block left or right. If we found that NB was negative or NA was negative, then we have a problem because they can only push on each other, they can't pull on each other. And again, the ground can only push, it can't pull. But NC we could draw in either direction and it would be okay. And for the block, we don't know its length or if it's a uniform piece. We will be unable to do a moment calculation on the block because of this. We don't know how long it is or where we do know where NA acts, but we don't necessarily know where the weight acts. But that's going to be okay. Based on our free body diagrams, I can get two equations, equilibrium equations, out of my first free body diagram. I have NC minus FA is equal to 0. I will have that the normal force is 491 newtons at A. I can't do a sum of moments. I don't know enough information about it, so I'll skip down to my second free body diagram. And I can take three equilibrium equations here. I know the radius, actually the two radii of the spool. In the x direction, I'll have my applied force of 300 plus FA minus FB. Of the weight down. NB up, NA down for my sum of forces in the y direction. From here, I can find that the normal force at B is going to be equal to 883 newtons. And my fifth equation, I'm going to call the center of this point O. If I take the sum of moments around point O, the normal forces pass through the center, the weight passes through the center. I'm going to have 0.2 times 300 from the applied force minus 0.4 times FA minus 0.4 times FB. If I look at the equilibrium equations, I have 5 equations for 5 unknowns. This is at the moment a solvable system. Keep in mind I do ultimately need to find the coefficients at A and B that would cause impending motion. But under the assumption of equilibrium, I can still solve for the remaining unknowns I have here. I found 2 of them so far, the normal forces. Now I want to find the rest based on these 5 equations before I get to the maximizing my frictional force. If I solve these, I'm going to find that for equilibrium, the force at B, or the friction at B has to be 225 pounds. And the friction at A, that should be newtons. And at A, it has to be negative 75 newtons. This negative value for equilibrium at A, for the frictional force at A, causes a contradiction in that, again, the friction force has to be positive. This means the only way for this to be correct is if FA were pointing to the right and negative. It can't be negative. Therefore, this scenario is not feasible. It's not going to be rotating around its center point. So since that's wrong, since FA is negative under this, that means this scenario can't be happening. So what must be happening is that the spool is sliding to the right. I would suggest making either like probably a new set of free body diagrams. But what's going to change is that, first of all, this we know is wrong. this has to point to the left. FA must be at the left, which in turn causes this FA to be to the right, which in turn says NC, to balance that out, should be pointing to the left. This is still okay. If it's sliding to the right, these should both be pointing to the left. The normal forces are now all okay. Under scenario B, these are now the slightly modified free body diagrams, which now will change some of our equilibrium equations. Number one, we have to switch these. The result is still the same. NC is still equal to FA. Equation 2 is still fine. That has not changed. Equation 3 changes slightly. 4 is still okay. And 5 will change. This is now a plus 0.4 FA minus 0.4 FB. Solving now this set of equilibrium equations, it does actually turn out that I get the opposite value or the opposite sign for FA, but that's not necessarily going to always be the case. Under this, I get FA as a positive 75 newtons. And again, NC is also 75 newtons. My 3 normal forces are positive, and my 2 friction forces are positive. So this is at least a feasible situation to have. So that means that it has to be on the verge of slipping at both of those contact surfaces. So FA is maxed out, so it's equal to mu A times NA. We know FA, we know NA. This tells us that the smallest mu A has to be, or could be, is 0.153. And simultaneously, the other surfaces have to be maxed out of friction. So mu B has to be at a minimum 0.255.